Welcome to the Spirit of Apollo. I'm your host, Mark Lesmeister. Today I'm going to put together the lunar module model, and then we'll talk a little bit about lunar orbit rendezvous and about the missions that first use the lunar module. So here is the completed lunar module. I have it in the legs folded up configuration, so I could show you how it will fit on the rocket itself. There's actually more pieces to this than you would think for such a small part of the overall model. Now, during launch, the lunar module rode on top of the S4B stage, and it was protected by a cone-shaped shroud. Once the astronauts executed their trans-lunar injection burn and started on their path towards the moon, the shroud would be ejected. Then the command and service module would use its reaction rockets to pull away from the S4B a little bit. They would turn around and extract the lunar module from the S4B. Now, it was in this configuration that the astronauts would travel to the moon. Once they got near the moon, the two of the astronauts would climb into the lunar module, and it would separate from the command module. The command module would continue to orbit around the moon, while the lunar module landed on the moon. After the astronauts did their exploration, they would launch from the moon using only the ascent stage of the lunar module, and they would have to meet back up with the command module in what is known as a lunar orbit rendezvous. Now, it is this orbital rendezvous that was considered to be the tricky part of the entire mission. For a better explanation of why orbital rendezvous is a little bit difficult to achieve and how the lunar orbit rendezvous was accomplished, let's take a look at some animations. Let's say the two spacecraft that are trying to rendezvous are in the same circular orbit. That means they maintain the same speed and so maintain the same distance between each other. You might think that all you have to do is fire the propulsion system on the rocket that's behind and it'll catch up to the spacecraft in front. But here's what happens if you do that. The rocket that fires its propulsion system ends up moving into a higher orbit and slows down. In order to understand what's going on here, we have to refer back to Newton's example of the cannon fired from the top of a high mountain. If the cannonball is fired at too slow of a speed to make it into orbit, the cannonball eventually hits the Earth again. If we launch the cannonball fast enough, the distance it falls in a given time is exactly equal to the distance the Earth curves away from the cannonball. The cannonball is in orbit. So, what if we launch our cannonball at a speed greater than the speed needed to stay at the same height above the ground? To understand that, we have to look at what happens to cannonballs when you launch them from the ground. Let's say the Earth is being invaded by giant bug monsters, and we're going to use a cannon to repel one of these bug monsters. We launch the cannonball, and the cannonball comes back down and hits the bug monster. When the ball is first launched, it has energy of motion, or kinetic energy. Because the Earth and the ball attract each other, it takes energy to pull them apart. That energy is stored in the system, like a stretched spring. Stored energy is called potential energy. Now, a rule in physics says that the energy always comes from somewhere. In this case, the potential energy comes from the kinetic energy, the energy of motion, that the cannonball had when it was launched. With less energy of motion, the ball moves slower. At the top of the motion, the ball is moving its slowest. As the ball comes back down, the potential energy gets converted to kinetic energy again, and the ball speeds up. The bottom line is, if you launch your cannonball with a certain amount of energy, the farther away from the Earth it gets, the slower it will be moving. So, getting back to our cannonball in orbit, what happens if we launch it with more speed than necessary to stay in orbit? Well, the fall of the cannonball will no longer exactly match the curvature of the Earth. The cannonball ends up getting farther away from the Earth. And when it gets farther away, it slows down. It gets closer, it speeds up again, and the process repeats. Our cannonball is now in an elliptical orbit. This kind of orbit is going to be key to understanding how two spacecraft can achieve rendezvous. To illustrate my example, I'm going to use a Apollo Command and Service Module and a Apollo Lunar Ascent Stage. In reality, though, the actual orbital rendezvous for these spacecraft was a little bit more complicated. In our simplified example, the Command and Service Module is orbiting around the Moon in a stable orbit, and at the appropriate time, the lunar module fires its ascent engines and takes off from the Moon. After reaching the desired height, the lunar module will fire its engines again and enter a circular orbit. At a precisely calculated time, the lunar module will fire its engines. It will enter an elliptical orbit called a Hohmann transfer orbit. And when it catches up to the command module, it will fire its engines again to enter the same orbit as the command module. The whole thing together might look something like this. NASA's first attempt at orbital rendezvous came during the Gemini 4 mission. In a somewhat makeshift attempt at rendezvous, astronaut Jim McDivitt piloted his Gemini 4 craft in order to attempt a rendezvous with the upper stage of the Titan II launch vehicle. This attempt was unsuccessful. However, during the Gemini program, NASA did manage to master the mechanics of orbital rendezvous. This was aided immensely by astronaut Buzz Aldrin, who actually wrote his doctoral thesis for MIT on the mechanics of orbital rendezvous and line of sight. The first mission to use the lunar module was Apollo 9. Apollo 9 practiced all of the orbital maneuvers that would be necessary to land the lunar module on the Moon, but they remained in Earth orbit. The first mission to actually accomplish lunar orbit rendezvous was Apollo 10. They carried a lunar module all the way to the Moon and did all of the procedures that would be necessary to land on the Moon, short of actually landing on it. They called it a dress rehearsal for the Moon landing that was to come with Apollo 11. Apollo 10 also holds several records. It is the fastest that any human beings have ever gone relative to the Earth, at 11,000 meters per second, or about 24,800 miles per hour. And they were the farthest away any human beings have ever been from their home, just because of the location of the Moon during the mission and the location of Houston, Texas, where the astronauts lived during the time when they were the farthest away in their orbit. Next time we'll put together the lunar landing scene, and I'll talk a little bit about Apollo 11. Until then, Godspeed.